Okay, so good afternoon. Let's continue this afternoon session of the Sixth Amazonian Symposium on Physics. And now we have Luiz Carlos dos Santos Leite that's going to talk to us about superradiance and quasi-bound states in a static, regular black hole spacetime. So please, Luiz, go ahead.
Hi everyone, it's a pleasure to be here today. And first of all, I'd like to thank the organizers for the opportunity to contribute to this symposium with this presentation. Well, today I'm going to talk about superradiance and quasi-bound states in a static regular black hole spacetime. This presentation is mainly based on a couple of works that have been done in collaboration with Sam Dolan from the University of Sheffield and Marco de Paula and Luis Crispino from the Federal University of Panama. This is the outline of my presentation. I will start with a brief introduction, then I'll move to the basic framework that we have assumed in our investigations. So we then move our attention to some results and we finish with some final remarks. Let me start this presentation by showing you a short animation. This by is Well, here we can observe the dramatic effect of the deformation produced by a black hole in the spacetime. Here we have some massive bodies deforming the spacetime for comparison, and here we have a black hole. We can notice that deformation produced by the black hole cannot be compared to the deformation produced by other massive bodies. This is because black holes are extreme deformation of the spacetime, where even light cannot escape. Mathematically, black holes can be described by solutions of the field equations of the theory of general relativity. And some of those solutions are known as the standard black hole solutions. The first standard black hole solutions was obtained by Schwarzschild in 1916, and the solution describes a static black hole and is completely characterized by its mass. We also have the so-called Harrison-Olson black hole solution. This solution describes a static black hole and electrically charged black hole. That is, the solution is completely characterized by its mass and the electric charge of the black hole. The most important solution from the physical point of view is the Kerr solution. The solution describes the exterior of a rotating black hole and is completely characterized by the mass and the angular momentum of the black hole. The charged version of the Kerr solution is known as the Kerr-Newman solution. This solution can be completely characterized by the mass, the electric charge, and the angular momentum of the black hole. Here we have an artistic illustration of a black hole, and I would like to call your attention to two parts of the black hole anatomy. The first one is the event horizon. Well, the event horizon is the boundary around the black hole beyond which events cannot affect an external observer. That is, the event horizon is a surface of no return and delimits this region of no return around the black hole. The other part that I'd like to highlight is the singularity, which is covered by the event horizon when we are talking about the standard black hole solutions. At the singularity, we lost predictability, and then physics breaks down. So the singularity poses a challenge to the theory of general relativity. Well, a common feature of the standard black hole solutions is the presence of a singularity covered by the event horizon. And in order to circumvent this problem, some proposals have been presented along these. One of those proposals is known as a regular black hole. A regular black hole is a solution that do present a coordinate singularity. That is, the regular black hole present an event horizon, the surface of Norton, but lack curvature singularities in the entire spacetime. So the singularity is no longer a problem when we are talking about regular black hole solutions. It's possible to obtain such regular black hole solutions within general relativity by coupling the theory with a source described by a nonlinear electrodynamics. And we have investigated a black hole solution obtained in this context. Well, the solution that we have used in our investigation was obtained by Ion Beato and Garcia, and we shall call for short the ABG solution or just ABG along this talk. Well, this regular black hole solution is described by this line element with this metric function. And we can observe that this uh, solution is completely characterized by its mass and its electric charge of the black hole. In order to have a regular black hole solution, the electric charge must to satisfy this condition. For this value of the electric charge, which is approximately given by this numerical factor, we have the so-called extremal regular black hole solution. And we have regular black hole solutions when the electric charge is smaller than this extremal volume of the electric charge. Well, we have investigated the propagation of a massive and charged scalar field around an ABG black hole. So we consider the Klingon equation, which is shown here in its covariant form, and here mu stands for the mass of the field, and the small q stands for the electric charge of the field. A is the electromagnetic potential, and phi is the electrostatic potential, which for the ABG solution is given by this expression. So we have separate variables in this usual way, obtaining a radial equation which is a Schrödinger-like equation. Here, this term is called the potential function and is explicitly given by this equation here. At the event horizon, our metric function goes to zero, and the potential function assumes a value which is related to the superradiance condition. Let's briefly recap what superradiance is. Well, in the case of a rotating black hole, a portion of the rotational energy of the black hole can be extracted through the interaction of the black hole with an impinged wave. Then we assume that we have a black hole described by the Kerr solution, that is, initially this black hole has a given mass and a given angular momentum, and we then have an incident wave that satisfies this condition, which is related to superradiance. He omega stands for the frequency of the incident wave, and m represents the azimuthal number of the wave, and this term here is the angular frequency of the event, right? Well, what may happen is that after being scattered off by the black hole, the scattered wave may possess a large amplitude than the incident one, and in the process, the black hole loses mass and angular momentum due to superradiance. An analogous phenomenon arises for charged black hole. Here we are considering a static charged black hole. That is, the solution is completely characterized by its mass and its electric charge. And initially, we assume that this black hole, this charged black hole, has a given mass and a given electric charge. So, for this case, the superradiance condition is now translated into this form. And again, omega represents the frequency of the incident wave, and the small q stands for the electric charge of the incident wave. And this term here is related to the electrostatic potential measured at the event horizon. So again, after being scattered off by the black hole, the outgoing wave may possess an amplitude larger than the incident one. But in this case, the black hole loses now mass and electric charge due to the superradiance. Well, we may combine superradiance with a confined mechanism in order to force the waves to continuously interact with the black hole, and then exponential growth arises, which means instability. Such configurations can be obtained by impose a surround mirror to the black hole, which is an artifact known as the black hole bomb, or in more naturally confined scenarios, such as in the case of massive bosonic fields, spacetime with a boundary plasma accretion disk or torus magnetosphere. The Heisenberg solution allows a superradiant instability when the field is confined in a cavity with a mirror-like boundary condition, or a space-time boundary. That is, if you consider that we have a um, a massive and charged scalar field around the Heisenberg solution, we may only have superradiant instability if we impose a surround mirror to this solution. In the case of ABG black holes, we have obtained that superradiance and quasibound states coexist in the same region of the parameter space, I will see later. Here we have the parameter space for Heisenberg black holes divided in three distinct portions. Here we have bound states but no superradiance, and here we have neither superradiance nor bound states. Here we have superradiance but no bound states. Here we show the mass coupling um, ratio to the charge coupling as a function of the charge to mass ratio of the black hole. And the solid red line represents the superradiance threshold, and this blue solid line represents the attraction repulsion threshold. That is, above these thresholds, bound states can form, and below the threshold, bound states cannot be formed. Now, now we show the parameter space for ABG black holes. What we may observe is that for ABG black holes, both superradiance and bound states coexist in the same region of the parameter space. And here, at this portion of the parameter space, we may have superradiant bound states, which are of interest when we are talking about instability. Well, in general, the quasibound spectrum have complex vertices. So we may separate the spectrum into its real part and its imaginary part. Now let's focus our attention to the real part of the spectrum. For the real part, we may use the so-called hydrodynamic approximation, which is basically assume the weak coupling regime. In this regime, the quasi-bound states extend to large radii. So, a robust understanding about the real part of the spectrum can be gained by expanding the radial equation at large values of the radial coordinates. So, by using this approach, a discrete spectrum arises for the real part, where this term here is just an order counting parameter, and we define the effective fine structure constant in this way, and the principal quantum number is defined in the usual way, where L is the wave angular momentum and N stands for the excitation number. Now let's move our attention to the imaginary part of the spectrum. The imaginary part determines whether the mode is growing with time, that is when the imaginary part is positive, or decaying with time, which occurs when the imaginary part is negative. When the imaginary part is null, we have stationary modes. That is, we have true bound states. Such true bound states exists lies on the superradiance threshold. Well, the imaginary part cannot be inferred by the far field expansion alone due to the details of absorption and superradiance depends on the near horizon region. So, based on previous works, we expect the imaginary part at low values of the mass coupling to grow with time in a polar law fashion with the following scaling, where this term here it's just a numerical fact. Before moving our attention to our results, let's briefly describe the numerical scheme used to obtain the corresponding spectrum. We have to impose bounding conditions according to the problem. Well, physical modes on a black hole spacetime must be purely going at the event horizon. So we have imposed such boundary condition in at the horizon. Quasi-bound states are especially located in the vicinity of the black hole. That is, those modes decay exponentially away from the black hole. So, having this in mind, we have imposed such bounding condition in the asymptotic flat region. So, by imposing such conditions, a quasi-bound spectrum arises with allowed frequencies. And in order to obtain such complex frequencies, we have used a Frobenius series and then integrate from the radial equation from the near horizon region up to a large radius, which is typically chosen as you can see here. Now, let's move our attention to our results. First, we show the radial profile, considering the fundamental mode and the lowest multiples. Here, we choose configuration in the parameter space, which lie within the superradiant regime. So, for all the modes shown here are in the superradiant regime. Okay. And we can notice that at the near horizon region, the monopole presents the large amplitude. Therefore, we expect that this mode will grow much more rapidly than the other. Here we show the radial profile now, considering some excited states. We can notice that, as in the hydrogenic case, the excited states present additional maxima and minima in the radial profile. Now let's start our discussion about the quasi-bound spectrum. Here we show the real part of the spectrum as a function of the mass coupling. We are considering here the fundamental mode and the lowest multiples. We can observe that for at low values of the mass coupling, the real part is well described by the hydrogenic approximation, as we expect. And as we increases the value of the mass coupling, we can notice that the ordering according to the angular momentum is maintained. Now we show the decay rate of our spectrum as a function of the mass coupling. Again, we assume the lowest multiples, and we can see that the growth rate at low values of the mass coupling and grows in a polar fashion as expected, then reach a maximum and then decays exponentially from that. This also we may note that the monopole presents the fastest growing growth rate. So these modes dominate instability. Now let's consider the spectrum for some excited states. We can see that the real part as a function of the mass coupling. We can notice that the fundamental mode presents the largest bind energy. And here we have the growth rate for the excited states. we can see that the excited modes appear to have the same power law index, but different coefficients. And we can see that at low values of the mass coupling, the growth rate increases in a parallel fashion as expected. Here we show the growth rate for large values of the mass coupling. For comparison, we show this guideline, and we can observe that for large values of the mass coupling, the growth rate decays exponentially. The exponential fall-off suggests that the near horizon region is separated to the potential minimum by a potential barrier. Well, let me finish our results by drawing a comparison considering the fastest growth rates. Here we assume that we have a massive and charged scalar field on ABG spacetime. Also, we assume that we have massive scalar and Broca fields on the curved background. Let me point out that here we assume that we have highly charged ABG black holes and we have rapidly spinning curved black holes. For the curved cases, we assume that we have co-rotating modes. And for the Broca fields, we consider the odd parity and the even parity. Well, comparing the results for the scalar fields, we can see that instability grows faster for a highly charged scalar ABG when compared to the rapidly spinning curved black hole. For external, when we compare the scalar ABG result with the program curve result, we can see that the even parity, for the even parity, the instability is faster than the scalar ABG. For external, the scalar ABG instability grows faster than the odd parity program curve case. Now, let me finish my presentation with some final remarks. Well, we have demonstrated that on ABG spacetime, superradiance and quasibound state coexist in the same region of the perimeter space, which means that we may have superradiant instability on ABG spacetime without imposing a surround mirror, which is different to the isonose case. For a fixed charge to mass ratio, we have shown that uh, at low values of the mass coupling, the growth rate increases in a polar law fashion and then reach a maximum and then decay exponentially from that. This exponential fall off suggests that the near horizon region is separated to the potential minimum by a potential barrier. Okay. We have found the maximum growth rate for the monopole state. As we have seen, the monopole mode has the largest bind energy and the fastest growth rate. And we have seen that higher multiples and excited states have slower growth rates. In order to finish, we intend to investigate in the near future fields of high spin on the ABG space-time. So that's all. Thank you for your attention.
Okay, so let's thank the speaker. Thank you very much. So, questions? Uh, in this case, the chairman cannot ask. It makes a little sense for the chairman to ask questions because I am co-author of the papers. Yes, go ahead, please, talk, Caio.
And hi, Luis, host. Thank you very much for the presentation. So I have a question regarding the time scale of the instability. Can you show again? So how do you compare this time scale with the usual one that exists in care? And so, if I'm not mistaken, the instability is the time scale is a very long time, right? 10 to minus something, right? Do you have it here?
Yeah, let me share my presentation. Um, you talk about
So the imaginary part of the mode, I think it would be, which order are we speaking of?
you say about the comparison with the curve.
Yeah, because in the care case we don't need the charge, right? So the charge here for you is what makes the role of the rotation. And then so you have a but you have a time scale that depends on the mass of the field. Right? The imaginary part depends on the mass of the field. So you have a right? Ah, yeah, there. Uh, okay. So it's in some cases it can be comparable. Okay. Yeah, Proca is I remember that Proca is a much shorter time scale as compared to the scalar case. But for you, yeah, for you, I think the maximum is similar to the scalar case in care, right? So you have so for the scalar case in care you have 10 to minus 7, and in your case you have 8 times 10 to minus 6. Okay, all right. So another question is, uh, do you have any clue about the end state of the evolution? So Carlos in the early in the week he mentioned about the evolution of clouds in care. And do you have any clue what happens when you consider back reaction and try to picture at least adiabatically what could happen to this cloud as they grow around these charged black holes?
Thank you for the question. So we must go into the nonlinear regime, right, to see what happens in this case. We conjecture that superradiant instability will make the exterior of the black hole evolve towards a quasi-stable configuration with a spherical symmetric scalar hat.
Okay.
But but indeed, we need to go into the nonlinear regime to to confirm if
But
if this.
yeah, I think sometimes you don't even need to go to the full nonlinear case because it depends a lot on how this transfer of mass and charge occurs, right? Because so it's like when you deal with accretion, for instance, you can say that the system is evolving through many equilibrium phases. So Carlos mentioned like for the scalar case, in some extreme situation, you have 20% of the mass of the total mass going to the scalar cloud. So if you have maybe something like this, you can treat perturbatively. But it's interesting because in this case, you have so it is a spherical cloud, right? The dominant one is spherical, right? Okay, thank you.
Kyle.
Okay, thank you, Caio, for a question. Thank you, Luis, for the answer. Any further questions? If not, so let's thank the speaker again.